Okay, time is ticking, and I believe you guys are everyone I'm gonna host today, and it's better to have less people so we can have a good conversation and discussion going on. So yeah, good afternoon, everyone. Thank you for having me here. Now my presentation starts. I'm Jielin from EMQ, and I'm also an open source enthusiast. So it's my honor here to present you NanoMQ and EKuiper, which both are two Linux Foundation Edge projects. I will walk you through the detail of them and to share some our experience of building products on top of that and for the automotive industry. It's just a short introduction of about who we are and what we do. So EMQ is a global company now, and we are taking open source really, really seriously. So even our flagship product, EMQX, it is also an open source project which has a decade of history. Now it's pretty popular now. It's being deployed worldwide. And all of our products have an open source version there. Okay, here is our category of today's content. I'm gonna set up the things to discuss why do we bother to reinvent the wheels, and why is it needed? And then we're gonna expand what is NanoMQ and what is EKuiper, and what you guys can benefit from it, and what we have done for the industries. And I'm gonna discover some mystery under the hood, so how NanoMQ EKuiper works, and how it is being adopted by the automotive. And also introduce you some real use case of how we build solutions for software-defined vehicles, including MQTT over QUIC. Here's a great topic for today. It's about everybody is talking about AI now, but it seems like there is one piece missing. So where is data? So GPU is data hungry. So you must serve data to your GPU at the right time and the right position. Otherwise, you only end up have expensive toys because of the I/O slow problem. Instead of buying more cards to add up computing powers, we need to focus on the new emerging bottlenecks, the slow I/O rate. So from the study made by Google and Microsoft, that has shown up that up to 70% of model training time is taken up by I/O, input-output. You put it another way, it means you are wasting your time and money, by 70%. So the way we resolve such issues in the cloud is by bypassing the CPU to link the storage with the GPU directly, which is basically called zero copy, thanks to the Mellanox. But however, the things are getting even worse for the edge, because the fragmented protocols and the asynchronous storage latencies really block us from unleashing real power of edge computing. So we got a more tough problem to deal with at the edge side. So there are also compatibility challenges, like this, which is not possible to repeat the same story just like what we did on the cloud. We don't have enough budget, we don't have enough resources, so we have to make use of what we have now to make every I/O counts. So I was trying to figure out some great wisdoms. So I do some research about in the previous days, the performance progress comes for free because basically the semiconductors release faster processor every year. We have been enjoying the free meals for decades. But now we are really hitting a power war here. You can see from the paradox picture here. So the single thread's performance is flattening out. The clock frequency has stabilized for more than decades. So it's not the same story as before. So the situation is even worse in the edge because due to the power efficiency and the heating up problems. But there's only one number keeping advancing, the number of cores. So this is what we have done in the past decades for the cloud computing to make taking advantage of multi-cores. So we need a new software infrastructure for edge computing as well that can chop the workload into different pieces and to let your multi-core system run them in parallelism. So just like an interesting manga here I draw. So this is what you got, a single core with a single DAC. It's a free meal in the past days. You don't need to worry about how to manage the different DACs. And however, once the workload being raised up and you got multiple DACs, the management staff workload gonna be overwhelming. You have to deal with how to let them run in parallel. Otherwise, you got one DAC doing all the work, others just sit and watch. It's pretty common for you to run some old days embedded software on the modern day CPU. But it's easy for saying, but it's hard to implement such a system, especially for embedded systems. We got a lot of high-level languages which has parallelism embedded in, but you cannot just migrate them to the embedded systems. We are talking about really real-time system here. Yeah, so we have to build something from scratch. I also find out that there's a computer scientist, Alan Kay, basically who he made object-oriented programming, but he was really against it. Actually, he says, "I'm sorry that a long time ago coined the terms objects for topics because it gets many people to focus on the less idea. The big idea is messaging. Yeah, the messaging is is the way out of this paradox. So also our EMQX broker, which is written by Erlang. Erlang is a system, it's a language inhabited on a virtual machine. The virtual machine inside has a very sophisticated actor model built inside. So I'm thinking of, could we just build something similar for the edge computing? So here is what I got. So principle number one, only share memory while messaging, not the other way around. That's the actor systems. So actor system basically is you build a virtualized actor, which take over codes, and he do something responsive to what the message you send him. Okay. Another big motivation is we wanted to preserve the beauty of interoperability and the edge-driven architecture for the edge computing. So imagine your devices, the number of your devices is growing, your business is growing as well, and you have to deploy more and more backend service. And each new service you deployed on the cloud, and each new device emerged on the edge, you have to create a new connection between them. So you end up a complex problem. So you have to build put a messaging broker in between of them to build a unified namespace. And same story gonna happen on the edge as well, in a vehicle, or for the industrial IoT case. You got multiple sensors multiple sensors on the site. You don't want to manage the connection one by one. So this is what we call the unified namespace across edge and cloud. So in draw a conclusion here, the paradigm is shifting for the edge computing. We need to take advantage of multi-cores. We move computation prior to move data. We unify data in motion and the edge for better interoperability. We build actors-based systems and reuse the data stream for edge event-driven architecture. Okay, the last motivation is about how to interpret the data. We all know edge computing will provide you low latency and save you bandwidth, blah, 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 cliches. However, we should also focus on the quality of the data, not only the scale. Unlike the previous days of the mobile internet, the data we deal with edge computing or we deal with internet vehicles, we deal with industrial IoT, the data is generated by objects, by machines. It's generated continuously, which is boundless and stateful. the data, at the very moment it was born, it has certain context of spatial and time awareness. The value behind it is diminished along with the time. So, yeah, we don't actually need raw data. We need information. We need to extract the knowledge behind it. We need to find the insight behind it. Okay, so this is actually what edge computing about. It's not just putting some fancy stuff from the cloud to the edge. Yeah. And more importantly, it also can save money for our customers. The data traffic costs a lot of money. It's useless to just transfer intact data from edge to cloud. It's just being lazy. Yeah, it's a repeat of copy paste. So, from what I see from our business case or from our customer there, they really want a feasible way to aggregate data and convert event data to event patterns, and by building a data transformation pipeline for the edge computing. So, yeah, it's a streaming engine. So here is our flowchart or our thoughts about the edge streaming. So therefore, here you got a streaming pipeline. Streaming pipeline here, which consists of several rules. Each of these rules could be really, really complicated or just a simple math equation. The rule, take a complicated case here as an example. So here is a complicated rules which has two data sources. They are from different sensors, and they could go both flows into an operator, or you can call it processors. Each processors could be just like average computing, or just a complicated hopping windows, which aggregate data for 30 seconds and to find out a peak value or any anomalies. Yeah. By doing so, we make pre-calculation and data cleansing, data filtering, and data interpolation possible for the edge. AI model is quite picky on the data you feed it to them. If you don't feed the correct data with a complete data sets, they won't give you the accuracy you want. So in this way, we really help our users to improve the efficiency and the performance of AI model running on the edge. Okay, above is our motivation. So here is how we make it possible. The first one is NanoMQ, which is actually it's a messaging bus which is targeted for unifying data in motion and edge. Here's a little bit of history of this project. So you might have heard of ZeroMQ. So ZeroMQ actually is built for a financial system at the very beginning, but the creator of ZeroMQ cannot get along with each other, so they diverged. So one of them exit to build another project called NanoMessage, and the picture over here, Garrett, he is also a friend of mine. He take over the project, build another next generation called NNG, and NNG is in collaboration with NanoMQ, and I'm also the maintainer of NanoMQ and the council member of NNG. So yeah, NanoMQ has been developed for 3 years, and in 2023 December, it has formally accepted by Linux Foundation Edge. So a quick look of what is NanoMQ. So it started as a messaging broker, but actually it's more than that. It can be used for building flexible network topology, and it has it is all synchronous I/O inside. Has a built-in vector models, which is why it is being performant, and it's PLC implemented. So it gives it high portabilities and compatibilities. Also, it provides you a lot of protocol converters and proxies, can bridging other protocols into your messaging bus. So we know parallelism is the salvation. So we build a new actor model with C language from scratch. So in code level, we hold two principles here to avoid data racing and stumping. So first one is no shared state, and the second one is no serialized code. We build different actors in the below and assign workloads to each of these actors, let them run parallelly. Yeah. So basically, we make it a lock-free architecture. So here's what we got from such architecture. It's compared to the traditional mosquito broker. Yeah, it performs far more better in 3 circumstances. Another one is EKuiper. Yeah, EKuiper is a universal edge streaming engine. Yeah, just to tackle the data boundaries and data stateful problem. So it is a general stream processing engine designed for edge computing. It has a friendly ecosystem support, very flexible rule engine inside. It's lightweight and provides you no-code circle engine, which make computation overloading and hot update on edge device possible by just upgrade your circle rules. So basically what it does is parsing the circle rules you deployed there and planning the stream pipeline and ingest the data from the source continuously and generate the data sinks via processors in a sequence. Yeah. As a streaming engine of edge, yeah, we're trying to preserve the familiar flavor from the cloud. It supports multiple data sources, including MQTT, CAN bus, HTTP, or database or files. Even video source is included as well. And you can apply a mathematical equation and statistical method API on the data and to aggregate the data. And you got your data sinks. And helps you to transform the data and enrich the data. Yeah. Okay. The boring part is over now. It's about the use case. So this dual combo here could fit in multiple cases actually, but here I pick automotive as an example is only because automotive is currently one of the most rapidly evolving industries in the world. Topics such as ride-sharing, connectivity, electrification, and automation shows the fastest development in the industries. Yeah, this includes more and extended influence of softwares and computer science expertise into the previous more mechanical engineering-based industries, which means this is a merging industry between IT part and the automotive part. In case you might don't know what SDV means. So SDV means software-defined vehicle applications. It has a different value proposition than that of the traditional vehicles. The car is no longer being finalized at the very moment it was manufactured. So the passenger and the driving experience are no longer determined by the mechanical or electrical systems, because the software is unlike hardware. It can continually improved, and it can be hot updated during the whole life cycle of vehicles. For example, it's like a connected vehicles applications, connect your vehicles to your apps, yeah, like a smart cockpit, like ADAS, of course. Also, now you know what the SDV means. You might wonder, yeah, how does it related to our topic today, or how NanoMQ and EKuiper and how we deal with it. So yeah, we're trying to seize the combining trend of SDV by bridging the gap of knowledge between the industry practitioner and open source software. So by deploying NanoMQ and EKuiper in the internal vehicles, it solves cross-domain data collections, converges all the data from different ECO domain controllers to your one central vehicle central computers. And perform the streaming calculation layer and to transmit the data back to the cloud. So it enables data observabilities and traceabilities. It allows you to do the remote diagnostic and bring in agile development procedure to the automotive world, which is a iterative software, and which this is dramatically reduced the development cycle of vehicles. Usually we need 4 to 5 years to release a new car to market, but after applying the new methodology here, the life cycle could be being reduced to 1 or 2 years. This is what is happening in China. So with the data closed loop platform being built, you can also have your corner case covered. I will explain more about what this corner case is. So here's a full picture of how a solution works. Across the vehicle and cloud, converging hundreds of sensors, dozens of ECUs in the vehicle to one connections, and consolidate that connection in between here with the quick transport. So extract essence out from the data by combining the time-spatial context and fuse it with other data sources. Let's look at an example first. So imagine you're driving a car, and the car at a speed of 200 miles per hour, and you hit the brake. There must be something wrong. But if you don't have a data closed loop, or you don't have data acquisition methodologies, then the OEM manufacturers had nothing to deal with such a complaint. You don't know what happened. So this is how it works. So the messaging bus collect the data across the domains ECUs. They are raw data still. The EKuiper ingests the heterogeneous data and perform a pre-calculation and sensor fusion on it. Extract information and knowledge from the raw data by string computations. And for example, you can join the data from camera with the data from the powertrain, and also the data from the BCM. BCM means body control module. So it records every action you did with the car. The streaming engine gonna intelligently analyze and identify the safety issues and allow the driver to take actions, or set up rules to allow to trigger the messaging queue here to aggregate all the data and translate back to the cloud. So so it's a triggering-based synchronization. So you don't need to synchronize a whole bunch of the intact data, raw data back to your cloud. You only synchronize those were valuable and valuable for covering the corner case and reconstruct the accident scene, and to retrain your models to enhance your ADAS functionality. Here is an example showing how the circle works. You just write, you only need to write a simple circles as a DBA here, and to make it, to let our stream engine parse the circle for you. And we're gonna do runs continuously to once the pattern is matched and everything works. Okay, another case here is a smart cockpit. So nowadays, cars is no longer just a riding tool. It's going to be an intelligent entrance for your daily life. So the background is, in order to achieve that, the interoperability is essential in IVI. IVI means infotainment system. So we need a broker seat inside or gateways in between, which is a soft gateway. So between the external device to bridge the ecosystem of IoT world to the automotive world. The IoT world device might be malicious, might be harmful to internal system. So broker here is also just like a firewall to provide the necessary accessibility controls. And to add on, these two functions, the two cases are both real business case here. The final part is about MQTT real quick. QUIC is one another big elephant in the room. You cannot ignore it. It has been widely adopted by other big commercial firms like Facebook, like Google. It has a lot of cool features here. I won't go through them one by one, but you can take take a quick look from our benchmark here. So yeah, QUIC really greatly improve the message latencies, the reconnect speed. And TCP is built for wireline communication. And QUIC actually is meant for wireless communication. And it's the perfect match with industrial IoT and especially the Internet of Vehicles. Okay. Here it is. This is how we build MQTT over QUIC. So basically, we build on the top of MS QUIC, which is built by Microsoft. Yeah, and our Nano SDK is the first commercial MQTT over QUIC SDK. NanoMQ is the first broker support MQTT over QUIC bridging. EMQX 5.0 is the first commercial broker support MQTT over QUIC. Okay, here's an insight of how MQTT over QUIC gonna change the game. So first one, while you need to deploy new SDK or deploy a new transport for your solutions, it's really painful because the device is all distributed. You have to OTA them one by one. But however, here if you put a NanoMQ in the between, you can have no code change, just use NanoMQ as a local bridging proxy. You can share the advantage of QUIC. And NanoMQ also utilize other advantage of QUIC, such as multi-string, multi-pass, zero RTT, and address migrations to overcome the poor network. And most importantly is it also has a built-in prioritization features. By mean prioritization is we mapping the QUIC string with the topic, and we allows you to prioritize your data traffic, which also means prioritize your business. By prioritizing your data traffic, you can preserve the bandwidth for the business critical data, which is a very welcome features for vehicle. Especially, yeah, here's the example. So this is an unmanned logistics company. They build autopiloting logistics services in the airport. So just those robotics patrolling around the airport, transport the luggage from one place to warehouse. Yeah, the service need to interact with the vehicles in real time to meet safety critical scenarios. However, the airport makes things worse. The EMC regulations basically says it's impossible for you to get a better quality of network coverage. And high-level autonomous driving needs low latency and high concurrencies. It seems like impossible to do so, but once you apply the MQTT over QUIC approach on it, yeah, we made what was impossible be possible now. So the data transfer rate raised by 20%, and now they can operate the business at the airport. That's all. Hopefully, you guys enjoy the show. Any question or have a good weekend?